Hi, I'm Nick Burek,
I'm Thomas Grable.
and this is the project that we've been working on for the Digilent Design Contest 2011.
Right.
So, our project running on a Nexys2 board from Digilent, and it's running with a Microblaze embedded processor core and some custom drivers that we've written to do the joystick interface as well as interface with the block RAM.
So just a little synopsis about how tile-based architectures work. These are classic, they date back from even before the Nintendo, but again, our architecture is based on the Nintendo picture processing unit. So what we do is we define tiles that are 8 by 8 pixels and we repeat them multiple times. This really saves on space due to redundancy. So instead of having a map of 640 by 480 pixels, we can reduce that down to 80 by 60 tiles.
And so the way that kind of works with the hardware is that we have block RAM set aside to store the data for each of the tiles, and each of those, like Tom said, is 8 by 8 pixels, and each pixel stores 8 bits worth of color information. And so in here, our example, we have a bunch of background blocks, and all of these seem to map up to that first tile, which we just have set to like a solid color, and then we have some other tiles that map to different tiles here. And then we also have these movable blocks here, which we can essentially move those anywhere, so they're not bound to a specific location like these background blocks. So this specific block, movable block here, we have mapped to 63, so the smiley face. And if we wanted to, we can move this 2 pixels to the left or 5 pixels to the right. And essentially that's how we created our frog in our Frogger game.
One of the major challenges that had to be overcome during this project was how to relate the software to the hardware. What we did was use memory mapped I/O. We developed a system of opcodes and instructions that could be related to from software. In software, we created functions that handled the low-level details and abstracted them, creating nice wrapper functions. We created several functions such as set pixels and setting movable block positions, so on and so forth.
So once the instruction gets outputted to the memory mapped I/O, we toggle a basically instruction ready bit, and when that goes from 0 to 1, the instruction gets decoded in the VHDL code here. And so essentially what it does is it looks at the 3 most significant bits there, 31 down to 29, and that determines what operation you're doing, if it's a set pixel or a move a block or something like that. And so essentially it just breaks this down into an if-else-if structure, and depending on what operation you're currently trying to do, it sets the appropriate data to the data that's wrapped in the 32-bit instruction.
So here you can see our hardware architecture configured to run yet another classic game. In this case, we're using the background tiles to store the paddle's graphics and the movable tiles to store the moving ball.